everyone. Happy Mother's Day. Hope everyone called their moms and told them that they love them, or if you don't like your mom, you called someone and told you love them. But let's get to it. More on pump selection. This one's probably, I think, the most helpful for your project because it will go over the graphs and how to use them on this pump stuff. But one thing let's go over on this idea of selecting your pump and the idea of what you need to look out for with pump. One thing that I haven't mentioned, but it's very critical for pumps and what's mostly that you care about in industry is this idea of cavitation in your pump. Now, cavitation is not ideal for something to happen, right? So why should you prevent cavitation? So I have some reasons here, and that's the idea that's when pressures become low enough or velocities become high enough that the liquid in the pump begins to boil. You get bubbles, and bubbles suck for pump systems. So we want to prevent it because we hate bubbles. I think that's good enough, right? We hate bubbles in pump lines, don't like them. The other one is at the location of cavitation, you have a bubble forming and then it cavitates, or it immediately just bursts or cavitates. So that causes gigantic acoustic pressure waves or giant, really forceful water jets when it occurs. You can look up videos on YouTube and I think they're really cool to look at. But so that's the other thing is, right, large acoustic pressure waves, right? And that just means, right, damage. It can damage the pump blades and the impellers on them. So cavitation is something you have to look out for because those are the two main ones. You don't want bubble lines in your pump, and you also don't want to lower the lifespan of your pump because where that cavitation occurs creates enormous forces, actually, if you do the calculations on the surface tension, I believe. So when does cavitation occur? Well, right, cavitation occurs on some thermodynamical principle, but it occurs when the pressure is equal to a special pressure of the liquid or the fluid you work with, and that's the vapor pressure. I think maybe you remember that in chemistry, but there are certain pressures that exist for liquids, or actually even a solid, where if your pressure is low enough, you begin to atomize or turn into a gas. So this is a certain pressure where you get a state change. So that's when it's going to cavitate. So now for our flow concepts of this idea of, right, this classic idea of I have some sort of pump, and usually this lower side, or the side where the pump will give elevation, is called the suction side. So these pressures are all occurring at the suction side of the pump. That's where you would measure the pressure. So keep that in mind, that it's on this side, not this side. So it's something great. This is sort of outlet, right? Anything else in here? So this is the pressure we consider about when we're talking about this non-positive suction head. So it's just something we define as engineers, NP. HS. It's quite old. I think that's too many letters for a math variable, but it's in everything, so keep that in mind. So that's going to be P1 over, right? I think you know how to get most equations in this class now. You just reweight Bernoulli's equation and get things. So what is this going to be? Minus. This is what's important. So non-positive suction head is equal to all this junk right here. Okay. Right. So There's really two balancing terms. You're looking at this value right here. You have this measured quantity of the head at the suction end. I know it's funny, but just keep a straight face. And then you have this fluid property that also is happening. So this is all dependent on the fluid. You could measure it in the static lab. This is about your system with flow involved in it. So, and the minus sign right here is important, right? Because this has the idea that you always want this to be positive. So net positive suction head. So you can understand you never really want to be here, because if your pressure actually is there, then you would have cavitation. So the least we should actually have is that this be positive. So that's why always we at least want to check this, right? You want the NPHS to be a positive quantity. So that's right. And you can always remember that, because net positive suction head. Suction head means I measure my values on the inlet side or suction side of the pump. So, right, if you have to remember to do that, don't measure it here, because you have to look at what's happening before you add that pressure energy in there. So clearly this is a very good result to have for a pump. I don't want to have that, because now I know for a fact, even at the most crudest approximation of how this pump works, right, I need to at least have this term be positive, because it would just be less positive if this wasn't true. So good starting points right here. Okay. So that's just the crudest thing to do about net positive suction head, right? But you never even want that net positive suction head to be really even close to zero, right? So really, we kind of want something like this, where there's some bound below here. Let's call it epsilon, right? You actually want it to be maybe far away from the zero, because you don't want, this is a variable term that's involved with these velocities and these pressures. So, right, if it's, right, so let's say this is, if you're just kind of like right here in this value of pressure, and you have these variations, right, if you ever get negative at one point, right, cavitation would occur, and then there's bubbles in the system, and then game over already. So you really want to make sure that this is at least kind of far above there, and sort of like, what's a really good lower bound for this to actually happen? So that at that point, if this is like, let's say time, right, what's really a working like lower bound on this besides just zero? Zero is the obvious one, but what's a really good working one? Where after, let's say, a suitable amount of time of you in an experiment room just running the pump at these values, you never see it even like perturbed down below zero. So figuring out what this actual sort of lower positive bound should be is this idea of a required MPHS. Okay, so that's this idea of what you have in the book and something like that. It's MPHS R. Okay. And this is like really where you can't be below. So this is actually even a function of flow rate. So you make a line for your pump that you've made, created, and now you're in the test trials of it, and you're actually running this to figure out what this really lower bound, so you'd have no cavitation occur. And then you can create this actual limit on the bottom of your graph. So you kind of have to do it with each data point. You have to run it, right? You have to run at a flow rate and go over many, many times and just see if there's not enough time has passed. There's no perturbations. You knock it, you bang it, but after there's no cavitation that will occur to a confidence that you agree with. So that's how you make this sort of required or given to you by the manufacturer, right? Definitely operate above this level in your net positive section head. Okay, so, right, these graphs, something like that, and right, remember, right, it's pretty easy to say this is actually in units, right? This is still units of head, right? It's still units of head, because it's made up of the head equation, but it just has this long variable name. Okay, so you can put it on this head, right? This classic graph we did last time. Remember what happened before is we had this sort of, right, we made that ideal line and talked about the other ones. This one ends up looking like it's kind of a line, and it goes up very slowly. Can't really see that, so let me just get this. So these lines, what they end up being for the pumps is they start like definitely don't ever operate, just can't even get it. Right, it's always going to be cavitating. And then kind of slowly, very, very slowly, it goes up with the flow rate. Okay, so that's just sort of what these look like. And importantly, too, this is like a really, really small scale. Just commonly in the ones you get. Like it really occurs sort of like in the lower end of these values, where your pump performance curve operates really, really high on the scale. So it's even hard to actually graph them on the same plot, which is why sometimes for these lines, what you will see of the graph is you will go on this plot right here. Here's the flow rate, and you'll see like here on this axis, it'll be like up to like 0 to 20. And then all of a sudden it will break off and like you'll have like maybe like a cut there right there because they're tying two axes together. And then you'll just start up again at like, let's say, right, 1,000 even. Like it is really far below and then tick along the way. So then down here, you'll get this, right, this lower bound on the non-positive suction head for the pump, meaning make sure you just operate above this, and then on the other top, you'll get that, something like that. And it doesn't really connect down there, but you can see you're kind of putting all the lines onto one exact plot. Okay. So that's the explanation of those graphs. One other concept is then you also have this idea of this actual. And this is like sort of what you're actually running the pump at, right? So the required is given to you by the manufacturers, and this is given to you from you doing some analysis to calculate it. So commonly, right, the idea is for all pump design, we really require that NP, sorry about that, non-positive. Oops. Okay, this is the biggest requirement we have for pumps, and that is that the actual so this is sort of what you calculate for the non-positive suction head in your designs, and then on this side you have that lower bound. Which is provided by the manufacturer. Okay, so in every instance throughout all of your pump designs, if you draw these piping systems, this is a check you have to see to make sure it's working. It could be even kind of rough, really, because this is sometimes really small. You could just get an order of magnitude idea on what this actual is for your design and see, oh, I'm good. So, only other subtlety on this non-positive section is what's poor performing on it, and it's this classic sort of comparing two designs where you have a reservoir going up to a tall reservoir, and then go up. Here's the pump, pumps it all the way up there. Fairly good, right? That's okay. And then the other one is this. So the only difference in here of this pumping system is this one is lower. This one matches the elevation on here, while this one is all the way at the top, and it's trying to suck the water all the way up instead of push the water. So sucking versus pushing. So this is good, and this is very bad. And this is bad because you're riding that non-positive suction head limit if you do it on that. Why do you do that? Well, we go back to the equation, and you can really see, what term is causing that. So this non-positive suction head actual, you can calculate it, right? So I have P1, and then you have a Z1, and then you can have losses Okay, so I think you appreciate with your presentations, right? How these losses for like city pipes or building pipes, right? This is just right, effectively zero. Okay, for P1 over here, if it's open to open, right? There's no change there. So sort of this negative sign right here, right? This Z, which you measure from here to here, this is Z1. Okay, that has a huge impact on this non-positive suction head, right? It's a minus sign, so you could really push your way all the way down to a negative non-positive suction head. Remember, any of these values, not even, right? You want this to be the case, but the higher you go up in Z1, the more this is just going to go decreasing and decreasing and decreasing and decreasing. So you're going to get to zero eventually, which is why you commonly, at least for design purposes, want to try to match this difference in that. So it's better to push than to pull. It's better to push the water up than to suck the water up, is my main takeaway for that.